In the year 2029, something enormous will sweep through our skies, closer than the moon itself, and yet most of us are not even looking. The headlines are all about a different traveler, a comet with an exotic passport, an emissary from beyond our solar system. That one bears the designation 3I, Atlas, a shimmering visitor trailing dust and vapor across the void. But the real story, the one hiding in plain sight, is far less glamorous and far more consequential. A 340-meter mountain of rock named Apophis. While the media dazzles itself with tales of interstellar intrigue, Apophis is quietly charting a path that will bring it 10 times nearer than the lunar orbit. 10 times. At a speed of 7.4 kilometers per second. Close enough that, on that April night in 2029, you could step outside and see it with your own naked eyes. A piece of celestial iron and stone, larger than a skyscraper, brushing past Earth in the closest planetary flyby in recorded history. And yet, here we are, treating the polite tourist like a potential threat, while ignoring the neighbor who is actually coming over for dinner. Tonight's story is not about why we're fascinated by 3I, Atlas. It's about why we're not talking about Apophis. The comet's credentials are certainly impressive. 3I Atlas carries the prefix 3I, marking it as only the third interstellar object ever identified in our skies. The I stands for interstellar, meaning it isn't bound to the sun at all, but instead follows a hyperbolic arc, like a stone from a slingshot. One pass around the fire, and then it is gone forever, hurled back into the abyss between stars, a one-night stand on a cosmic scale. It joins a tiny and exclusive club. 1I Oumuamua, discovered in 2017, and 2I Borisov, detected in 2019. Each time one of these wayfarers appears, astronomers see a frozen message in a bottle, a time capsule from some other stellar neighborhood. They have drifted through interstellar space for millions, perhaps billions of years before wandering into our domain. The Hubble Space Telescope has been following Atlas since its discovery, its sensitive optics catching the faint teardrop of dust that surrounds the comet's nucleus. Under the warming touch of our sun, ices sublimate, releasing streams of gas that sculpt the classic coma and tail, a luminous brushstroke across the night. By every measure, Atlas behaves exactly as the textbooks say it should. A stranger enters, warms, brightens, and departs. Beautiful, yes. Dangerous, no. On the 30th of October 2025, the comet will make its closest approach to the Sun, a tidy 1.4 astronomical units, about 210 million kilometers, just inside the orbit of Mars. From Earth's perspective, that geometry places us safely aside. No chance encounter, no near miss. On the 19th of December of that same year, Atlas will be about 268 million kilometers from Earth. To put that distance in perspective, you could fit the moon into that gap nearly 700 times over. NASA's Planetary Defense Coordination Office and the European Space Agency are unequivocal. No threat, they repeat. Harmless pass. Not euphemism, not hedging. Certainty, built on centuries of orbital mechanics. And yet the comet has stolen the spotlight. Amateur astronomers polish their lenses, ready to catch the flare in November skies just after perihelion. Journalists spin headlines about alien visitors and interstellar mysteries. Meanwhile, in the quieter backrooms of planetary defense, the work that truly matters goes unnoticed. Because danger in space is not about rarity, it is about proximity and probability. The irony is sharp. We gaze in awe at an object that will never come closer than hundreds of millions of kilometers, while in the same breath we scroll past the reports of near-Earth asteroids, chunks of rock and metal that routinely brush past within lunar distance, dozens of them every year. objects that were born from the same primordial disk of dust and gas that gave birth to Earth. They are, in the cosmic sense, our siblings. And some siblings come uncomfortably close. Think about it. The nearest that 3I Atlas will come to us is 268 million kilometers. Compare that to the Moon's 400,000-kilometer orbit. We measure that gap in hundreds versus hundreds of millions. The difference is staggering, yet when interstellar visitors appear, they are dressed up as exotic celebrities. We whisper about alien origins, about strange chemistry. When asteroids pass near the Earth-Moon system, the press releases are filed away in technical journals and government archives. Which category poses the true risk? The answer is obvious. Somehow, the public conversation has it backwards. None of this diminishes the scientific treasure that Atlas carries. These objects do matter, profoundly, for astronomy. The dust and gases they carry can reveal what kinds of materials crystallize in other planetary nurseries, whether organics that seed life are common in the galaxy, how comets endure across epochs of interstellar wandering. Every measurement is a window into the unknown. But these revelations, however profound, do not help us learn how to protect our world. They cannot prepare us for the impacts that have already reshaped Earth's history. The record is stark. 66 million years ago, the Chicxulub impactor slammed into what is now Mexico, ending the reign of the dinosaurs and altering the trajectory of life itself. In 1908, the Tunguska event flattened 2,000 square kilometers of Siberian forest in a single morning, an airburst that lit the skies as far away as Europe. In 2013, a meteor over Chelyabinsk shattered windows across an entire city, injuring more than 1,000 people. None of these were interstellar oddities. They were ordinary residents of our solar system, asteroids and fragments that happened to cross paths with us at precisely the wrong time. The asteroid that threatens us next will not come from another star system. It will be an object like Apophis, local, familiar, orbiting our sun on a path that occasionally intersects ours. That is the danger. That is what keeps planetary defense experts awake at night. So yes, while Atlas streaks toward the sun at 40 kilometers per second, shedding gas and dust, making itself visible in dawn skies, we should look up and appreciate the rare spectacle. But as we marvel, we must also remember, the real hazards are quieter. They have no luminous tails, no hyperbolic arcs. They circle the sun on repeat, waiting for the geometry to align in precisely the wrong way. This is the lesson Atlas offers, though it was never its purpose. It reminds us to distinguish between what is spectacular and what is dangerous, to remember that beauty can distract us from risk, and to understand that the object which may one day alter the fate of our civilization will not come trumpeting in from the stars. It will be one of our own kin, an asteroid born of the same dust that once made Earth, following its ordinary elliptical path until the night when that path crosses ours. And before we turn to Apophis, before we confront the asteroid that genuinely rattled the experts, we must hold this paradox in mind. The interstellar wanderer teaches us wonder, but the real story is survival. Part 2. 3I Atlas. What it teaches and what it doesn't. Let us begin with the obvious. 3I Atlas is remarkable, but the reasons for its scientific value have nothing to do with planetary defense. Its orbit will never cross ours. Its velocity is too high, its trajectory too steep. This comet, moving on a hyperbolic escape path, is destined to vanish back into the dark between stars. The questions it answers are profound, but they are not the questions of survival. So what exactly makes Atlas worth our attention? The first clue comes from its scale. Astronomers using Hubble have placed an upper bound on its nucleus at around 5.6 kilometers in diameter. though the actual size may be smaller once the brightness of its expanding coma is stripped away. That makes it modest compared to some of the asteroids that haunt Earth's neighborhood. In fact, many near-Earth objects, the ones that trouble planetary defense experts, are larger. But size, in this case, is not the prize. The prize is composition. Here is a chunk of ancient ice and dust that has wandered the void for millions, perhaps billions, of years. It has endured cosmic rays, endured the deep freeze of interstellar space, endured epochs of wandering with no star to call home. If it carries organic molecules, then it carries whispers from the system where it formed chemical fingerprints of alien nurseries of planets, records of what other suns produce in their cradles of dust. Astronomers see it as a once-in-a-lifetime opportunity, a frozen capsule from beyond our borders. That is why telescopes across the globe, and above it, are turning toward Atlas. The James Webb Space Telescope is taking spectra of its reflected light, trying to decode the faint chemical signatures of molecules embedded in its ices. Ground-based observatories, scattering across latitudes, are measuring polarization of sunlight bouncing off its coma, searching for patterns that betray the texture and size of dust grains. Radio telescopes are listening for emissions from specific gases as they boil away under solar heat. Every observation is a thread, woven together into a tapestry of information before the object vanishes forever. This is science in real time, international and cooperative, a race against the clock to squeeze knowledge from a transient visitor. But we must also be clear about what 3I Atlas does not teach us. It does not teach us how to defend the Earth. Its orbital geometry ensures irrelevance to planetary defense, not just now but forever. Interstellar objects, by their very nature, are unhelpful in scenarios of impact. They move too fast. Their paths cut through the solar system like arrows shot from afar, close approaches measured in astronomical units rather than Earth radii. They are fireworks in the distance, brilliant, mesmerizing, but harmless. Contrast that with the objects that planetary defense actually worries about, near-Earth asteroids. These bodies follow elliptical orbits. They come around again and again, sometimes every few years, sometimes on century-long returns. They do not vanish after one pass. They linger, and their orbits evolve, nudged by gravitational interactions with planets, or by subtle forces like the Yarkovsky effect. The tiny recoil produced as an asteroid absorbs sunlight and re-radiates it as heat. Over decades, even centuries, these nudges can shift a trajectory from harmless to hazardous. That is where mathematics, probability, and constant tracking become critical. Risk in space follows a brutal arithmetic: proximity times size times probability. By that metric, Atlas is all but disqualified. Its proximity is negligible, its probability is essentially zero. It is spectacle without substance, dazzling without danger. Yet media coverage does what it always does. The discovery is announced with breathless awe: alien visitor from another star. Somewhere, in the 7th paragraph, a disclaimer: no threat to Earth. Then, weeks of speculation about strange chemistry, unusual shapes, mysterious origins. What remains missing is a conversation about the objects that actually matter, the asteroids that slip past within lunar distance every month, the potentially hazardous asteroids, PHAs, that are large enough, close enough, and persistent enough to justify continuous monitoring. NASA's Center for Near-Earth Object Studies, CNEOS, keeps track of them. Their tables are public, dense with names like 2024 PT5 or 2025 RX12. Most are small, none are mysterious, and so they make no headlines. But these are the ones planetary defense cares about, because they are the ones we might one day have to deflect. Deflection is not science fiction. It has already been tested. In 2022, NASA's DART mission hurled a spacecraft into the asteroid moon Dimorphos. The result exceeded expectations. Its orbital period shortened by 32 minutes, 3 times more than the minimum required to call the test a success. For the first time in history, humanity deliberately altered the trajectory of a celestial body. That is planetary defense in action. And the story continues. The European Space Agency's Hera mission, launched in October 2024, is now on its way to Didymos and Dimorphos. By late 2026, it will study the aftermath of DART's impact in exquisite detail, measuring crater size, mapping ejecta, analyzing structural changes. All of it is about one thing: understanding how near-Earth asteroids respond to our attempts to push them. None of it involves interstellar comets. Atlas, on its hyperbolic escape path, contributes nothing to this field. You cannot deflect what is already fleeing at escape velocity. This distinction matters not just to scientists, but to the way we talk about risk. The exotic and the dangerous are not synonyms. Atlas captivates our imagination because it is alien, literally. It carries chemistry from elsewhere, a cosmic import. But imagination is not the same as probability. The threats that matter are the ordinary ones. They are the S-type asteroids, built of silicate rock and nickel-iron metal. They are the C-types, dark and carbon-rich, carrying water and organics. They are the Q-types, fractured remnants of larger bodies, shattered in ancient collisions. Ordinary categories, dull taxonomies. Yet within these types lie the true risks, because these are the objects that move in our neighborhood. These are the ones that share the sun with us, cross our orbit, and occasionally approach too close. Meanwhile, the observing timeline for Atlas underscores its fleeting irrelevance to planetary defense. For the rest of this September, it will glow faintly in evening skies. By October, it will slip into the sun's glare, lost from sight. In November and December, it will emerge again, brighter, fresh from perihelion, before fading into darkness forever. That is the rhythm of interstellar visitors, brief apparitions, data collected in hurried windows, then gone. Near-Earth asteroids, by contrast, come back. They reappear on schedule. They can be tracked across decades, their orbits refined, their physical properties measured again and again. They are not dazzling fireworks. They are reliable, predictable neighbors, and precisely because of that predictability, they are the subjects of real defense planning. So yes, enjoy the show that Atlas will soon put on. Celebrate the fact that humanity, with its instruments and ingenuity, can now detect objects that arrive from other stars. Marvel at the coordination that allows observatories on multiple continents to chase a moving speck across the void. This is human achievement, worthy of admiration. But let us remember, the real work of planetary defense is unglamorous. It is the patient cataloging of asteroids with forgettable names. It is the modeling of orbital perturbations, decade by decade. It is the testing of kinetic impactors and the planning of deflection strategies for objects that truly could one day strike Earth. Because while we stand entranced by a comet that poses no threat, the true hazards are quietly circling, bound by the same sun as us, following elliptical orbits that sometimes bring them far too close to home. Part 3. Reframing risk. Known neighbors versus rare visitors. The universe has a way of exposing our blind spots. We humans are mesmerized by the extraordinary, yet lulled by the familiar. The paradox is simple. The visitors from distant stars inspire fascination but almost never danger, while the objects born in our own solar system, our true neighbors, pose the risks we ought to fear. Familiarity breeds not just comfort, but complacency. And in matters of planetary defense, complacency can be fatal. So let us redraw the map, build a taxonomy of what really matters. The phrase near-Earth asteroid, or NEAR, carries a specific definition. These are objects whose orbits bring them within 1.3 astronomical units of the Sun, roughly 200 million kilometers, close enough to cross, or nearly cross, the orbital path of Earth. Within this domain lies a cast of characters divided into families, 4 groups defined not by imagination but by mathematics. The Aten group, for instance, orbits mainly inside Earth's path, with semi-major axes under 1 AU, but aphelion distances that extend just beyond our orbit. They dwell closer to the Sun but still cut across our road. The Apollo group follows orbits with axes greater than 1 AU but perihelion distances that dip beneath Earth's track. These are the classic crossers, weaving in and out of our lane like celestial commuters. The Amor group approaches from the outside, swinging inward with perihelion distances between 1.017 and 1.3 AU, close enough for worry. Finally, there are the Ateras, rare bodies that circle entirely inside Earth's orbit, yet can graze our path when they venture outward. From these families emerge the class of objects that matter most, the potentially hazardous asteroids, or PHAs. Their definition sounds dry, bureaucratic, 2 conditions that boil down to something visceral. To qualify, an asteroid must come within 0.05 AU of Earth's orbit, 7.5 million kilometers, a stone's throw on planetary scales, and must be large enough to matter, with an absolute magnitude of 22 or brighter, corresponding to a diameter of about 140 meters or more. That size is not chosen at random. A 140-meter asteroid carries sufficient kinetic energy to level a city, to kill millions, to cascade disruptions across global society for years. For comparison, the Chelyabinsk meteor in 2013, a mere 20 meters across, injured more than 1,500 people with a shockwave alone. Scale that up by a factor of 7, and you are no longer looking at broken windows. You are staring at a catastrophe. This is where risk becomes personal. NASA reassures us that Apophis, the skyscraper-sized asteroid that will skim past us in 2029, poses no danger for at least a century. But that statement applies to one object. The broader population of PHAs contains over 2,000 known members, and the count grows every month as telescopes refine their sweeps. Each new detection is another potential headline deferred, another piece of orbital calculus waiting to align in the wrong way. The discovery curve tells its own story. In 1990, astronomers knew of fewer than 200 NEAs. By 2000, that number had climbed above 1,000. Today, we have catalogued over 34,000, with about 3,000 new entries per year. For the largest bodies, the kilometer-class asteroids capable of global extinction, we are nearly complete. 90% are found, and none pose a near-term threat. But the smaller class, the so-called city killers, in the 100 to 500 meter range, remain elusive. Tens of thousands may still be out there, unseen, waiting for the moment when geometry and gravity conspire. The cavalry is coming in the form of the NEO Surveyor, an infrared space telescope purpose-built for asteroid hunting. Scheduled to launch no earlier than late 2027, it will peer into wavelengths that reveal the dark, carbon-rich objects invisible to optical searches. Its mission: to uncover the shadows that still haunt our skies. The statistics cut 2 ways, reassuring and unsettling at once. On any given day, multiple small NEAs slip past within the Moon's orbit. NASA's automated systems churn out these close approach tables daily, calculating trajectories with mechanical precision. Most of these objects are tiny mere boulders that would incinerate harmlessly in our atmosphere. But not all. Every so often, something larger sneaks through detection, a reminder that our survey net is still porous. Here lies the real nature of asteroid risk. It is not about a single object with a terrifying trajectory. It is about cumulative exposure. Each near miss, each close approach, carries a sliver of probability. Over centuries, over millennia, those slivers accumulate into certainty. The rocks that wander safely by today may return in altered form tomorrow. Because orbits are not static, they evolve under invisible hands. Jupiter's immense gravity tugs at passing NEAs, reshaping their paths over spans of decades. The subtle whisper of sunlight itself exerts a force, the Yarkovsky effect. Imagine an asteroid rotating, one side warmed by the sun, the other cooling in shadow. As it re-radiates heat, photons carry away momentum, creating a tiny thrust, imperceptible in a day, but inexorable across centuries. That soft push can shift an orbit from safe to hazardous or, if luck holds, from hazardous to safe. And this is why 3I Atlas is not just irrelevant to planetary defense but actively misleading as a mental model. Its hyperbolic trajectory makes it immune to these forces. It will not circle back. It will not be perturbed into danger. It is a one-time showpiece with zero cumulative risk, the very opposite of what we should fear. Near-Earth asteroids, by contrast, are dynamic. They are persistent. They evolve. An Apollo that misses us by millions of kilometers this decade might return tighter, faster, altered by a gravitational keyhole or a subtle thermal nudge. What is safe today may not be safe forever, and therein lies the challenge. Planetary defense is not about the spectacular. It is about patient vigilance, century after century, tracking the incremental drifts that can one day converge into collision. This reframing of risk forces us to look away from the dazzling headlines, to see instead the quiet shadows of our own solar system. The near-Earth asteroids are not alien. They are kin. They are built from the same dust that built Earth itself. And yet, unlike the rare tourists who pass once and vanish, these neighbors linger. Their presence is continuous, their potential impact cumulative. So when we marvel at 3I Atlas, let us do so with clarity. Enjoy its brilliance, study its chemistry, but never confuse spectacle with danger. The true threats circle us every day, embedded in the familiar rhythms of our own star's family. No neighbors, not rare visitors. And it is they, our cousins in stone and metal, that will determine whether our species endures the next 100 million years or not. Detecting and measuring the Yarkovsky effect is an act of patience. It is the science of shadows and whispers, requiring years, sometimes decades of meticulous astrometric observation. Astronomers point their telescopes at a faint dot against the starry background, night after night, charting its drift with an accuracy of mere fractions of an arcsecond. Over time, they assemble a baseline long enough to reveal something astonishing. Sunlight itself can push an asteroid. Each day, heat absorbed and then re-emitted as infrared radiation acts like the exhaust of a minuscule thruster. Over centuries, that invisible force nudges orbits by kilometers, shifting futures from harmless to hazardous. For interstellar visitors like 3I Atlas, such work is impossible. They pass once, never to return, moving too quickly for this kind of patient tracking. But for near-Earth asteroids, this is the essence of planetary defense, the unglamorous, headline, free discipline of watching, measuring, recalculating, no alien chemistry, no mysterious origins, just the quiet accounting of rocks that share our orbit. And yet, that patient discipline has already proven its worth. It gave us the ability to dismiss 3 Atlas, as a harmless curiosity. It gave us the tools to separate spectacle from danger. It built the global infrastructure of surveys, data pipelines, and cooperative networks that let us identify real threats in time. Which brings us to the asteroid that crystallized all these lessons, the one that taught scientists, journalists, and the public how risk communication must unfold in the age of planetary defense. Its name is Apophis. The year was 2004 at the Kitt Peak National Observatory in Arizona. Astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi were scanning the sky in a routine survey for near-Earth objects. On their images appeared a faint moving speck, another dot in the endless procession. At first glance, there was nothing remarkable, but when its orbit was computed, the numbers whispered chaos. This object was catalogued as 2004 MN4, later to be named 99942 Apophis, after the Egyptian serpent god of destruction. The choice of name, though made through standard conventions, would soon seem prophetic. Initial orbital solutions suggested that Apophis was on course to make a very close approach in April 2029. And not just close. Early estimates gave it nearly a 3% probability of impact. That number may sound small, but in planetary defense terms, it was unprecedented. By December 2004, calculations suggested a 2.7% chance that Apophis could strike Earth on Friday the 13th of April, 2029. The irony was chilling. A god of chaos, arriving on the most superstitious day of the calendar. The Torino scale, which ranks asteroid threats from zero hazard to 1-0 certain global catastrophe, assigned Apophis a level 4. Never before had a real object received such a high mark. The world took notice. Astronomers mobilized. NASA and ESA expanded their observation campaigns. Telescopes worldwide turned their gaze on Apophis whenever it crept into view. Radar beams from Arecibo in Puerto Rico and Goldstone in California painted it with microwaves, mapping its shape, rotation, and reflective surface. They revealed a stony S-type asteroid, elongated about 340 meters long and 150 meters wide. Its surface, dark and muted, reflected only a quarter of incoming sunlight. It was large enough, solid enough, and fast enough that if it ever struck Earth, it would release energy equivalent to hundreds of megatons of TNT, an order of magnitude greater than the most powerful nuclear test in history. Not extinction, but devastation. A regional disaster. Millions of lives, entire nations, potentially at stake. But science is a process, not a verdict. With every new observation, the uncertainties in Apophis's orbit narrowed. The nominal probability remained alarming, but the error bars shrank. The breakthrough came when Don Yeomans and his team at NASA's Jet Propulsion Laboratory searched old sky surveys and found pre-discovery images of Apophis dating back to March 2004. These faint archival dots extended the observational arc, allowing a much sharper prediction of the asteroid's future path. By 2005, Apophis had a favorable apparition bright enough for extensive ground-based tracking. With that data, astronomers could rule out the catastrophic 2029 impact. By 2006, the probability had collapsed to 0. Apophis would pass Earth extraordinarily close, just 31,600 kilometers above the surface, within the orbit of geostationary satellites, but safely. Still, the story wasn't over. The concept of gravitational keyholes lingered. These are tiny corridors of space, narrow as a city block, through which an asteroid can pass during a flyby. If it threads that needle, the gravitational tug of Earth can redirect its orbit into a future impact trajectory. For Apophis, One such keyhole could have set up a strike in 2036. The probability was small, but not negligible. For years, the asteroid carried a shadow of uncertainty. Resolving that uncertainty required nothing less than detecting the Yarkovsky effect on Apophis itself. Only by measuring the slow thermal drift could scientists know whether its orbit would evolve toward or away from that keyhole. The task demanded a level of precision rarely attempted, measuring Apophis's position relative to background stars to an accuracy of hundredths of an arcsecond. The answer came in 2021. Independent teams confirmed the Yarkovsky drift, a subtle shift of about 170 meters per year in its semi-major axis. Small, but decisive. The drift moved Apophis away from the keyhole, ruling out not just 2036, but any impact in the next century or more. And just like that, the serpent of chaos transformed from a looming threat into a once-in-a-civilization scientific opportunity. On the 13th of April 2029, billions of people across Earth will be able to step outside and see it with their eyes. A mountain of rock sailing silently across the sky, closer than the orbit of our satellites, harmless but unforgettable. What had once been our most precisely predicted doomsday is now our most precisely predicted spectacle. The lesson is profound. Early scary numbers are not mistakes. They are the first approximations, honest reflections of uncertainty. As the data accumulates, probabilities shrink or grow until clarity emerges. Communication must capture this nuance. Alarm is natural, but refinement is inevitable. This is the process of planetary defense functioning exactly as intended, from uncertainty to vigilance to certainty. Apophis is still dangerous in the abstract sense. A body 340 meters across, passing within the realm of satellites, is no trivial neighbor. But the danger is no longer tied to a date. It is a general hazard, one among thousands. What Apophis taught us is how to navigate the psychology of risk, how to move from sensational headlines to sober confidence, and how to transform fear into preparation. And so the tale of Apophis is not ending but beginning. The 2029 flyby will be a gift to science. Radar mapping of unprecedented detail, spacecraft missions that may swoop alongside, the chance to study how Earth's gravity reshapes an asteroid's spin and surface in real time. For planetary defense, it will be a live-fire drill, a rehearsal for the day when the numbers do not collapse to zero. Because one day, the serpent will not miss. Not Apophis, but something like it. The real lesson is not that we are safe, but that vigilance works. On the 13th of April 2029, at 21:46 UTC, Apophis will blaze across the skies of Europe and Africa, brighter than most stars, silent, massive, breathtaking. Humanity will watch together, marveling not at an alien visitor but at a familiar neighbor, one we have tracked, measured, and, for now, survived. The age of planetary defense has already begun. Part 4. Why 2029 Matters Anyway. On the 13th of April 2029, something will happen that has never before occurred in recorded human history. A mountain-sized asteroid will skim past Earth, closer than our highest satellites, close enough to see with the naked eye. Its name is Apophis, and though the world is safe from impact, the encounter will become a watershed moment for planetary science, public imagination, and the future of asteroid defense. Picture the scene. A 340-meter-long mass of rock and nickel iron, streaking silently across the heavens, passing at a distance of 31,600 kilometers above the surface. That is not just closer than the Moon, it is closer than the ring of geostationary satellites, orbiting at 35,786 kilometers. Apophis will thread the narrow gap between Earth and its infrastructure, flying through the same orbital zone where our communications, weather, and navigation satellites keep vigil. Never in modern times has an object of comparable size come this close. The date itself, Friday the 13th of April, adds a mythical resonance, a day steeped in superstition now reborn as a milestone in science. For much of Europe, Africa, and Western Asia, the flyby will be visible to the unaided eye, a moving star gliding across the night, a reminder that our planet does not spin in isolation but amid a dynamic, sometimes dangerous cosmic neighborhood. But visibility is only the beginning. At this proximity, Earth will do more than watch Apophis, it will act upon it. The asteroid will enter Earth's gravitational well and be reshaped by it. Tidal forces will stretch and compress its elongated body, tugging at surface boulders, straining weak points in its interior, possibly altering its spin. This is not an abstract thought experiment. Models predict that Apophis rotates once every 30.6 hours, a languid tumble through space. Earth's pull may speed this up, slow it down, or tilt its axis, depending on the complex interaction of shape, density, and trajectory. Imagine a bag of gravel suspended in space. If you squeeze it from one side, rocks shift, dust spills, fresh surfaces appear. Most asteroids are not solid monoliths, but rubble piles, collections of rocks bound loosely by gravity. If Apophis is such a structure, its encounter could trigger landslides, slumps, or avalanches across its surface, revealing pristine material untouched for millions of years. At the moment of closest approach, 2146 UTC on the 13th of April, Earth's gravity will be about 50 times stronger than the asteroid's own. That tidal stress will act like a wrench. Will Apophis withstand the strain? Or will it shed part of itself in the encounter, scattering debris as it departs? We do not yet know. But for planetary scientists, this uncertainty is a gift. A natural experiment unfolding in real time, visible from Earth, measurable with our most advanced instruments. The preparations are already vast. Ground-based radar systems, Goldstone in California and Green Bank in West Virginia, will bounce signals off Apophis, producing images with meter-level resolution. These radar portraits could reveal surface boulders, ridges, or even landslides triggered during the flyby. Optical telescopes will monitor its brightness and color, searching for changes that hint at freshly exposed surfaces. If the asteroid's rotation alters, observatories like the Catalina Sky Survey and Linear will detect the subtle shifts in its light curve. Every data point matters. Understanding how rubble pile asteroids respond to tidal stress is not mere curiosity, it is the foundation of planetary defense. If humanity ever needs to deflect a hazardous asteroid, we must know whether we are pushing on bedrock or squeezing a bag of rocks. Apophis offers the first large-scale natural test case. Yet the significance of 2029 extends beyond the laboratories. It is also about public engagement. Unlike most astronomical events, which require telescopes or ideal conditions, Apophis will blaze bright enough for millions to see unaided. Amateur astronomers are planning coordinated campaigns, their small telescopes adding to a global network of professional observatories. The International Astronomical Union's Minor Planets Center will coordinate incoming data, creating the largest collaborative dataset ever assembled for a single asteroid flyby. Educators are preparing too. Schools will use Apophis as a living case study in gravity, orbital mechanics, and planetary defense. For once, textbooks and classroom lectures will point not to abstract diagrams, but to something visible in the sky overhead, a 340-meter object that once terrified scientists, now transformed into a teaching tool. Even satellite operators are preparing. Though there is no credible risk of collision, Apophis's passage through the geostationary region will be treated as a full-scale exercise in space situational awareness. Agencies like the European Space Agency will simulate response protocols, monitoring trajectories, and preparing minor adjustments if necessary. In a world increasingly crowded with satellites and debris, the encounter offers a rehearsal for managing orbital risks in real time. Some scientists are even exploring whether Apophis's gravity might nudge Earth itself, not in any catastrophic way, but subtly. Could the asteroid's passage cause imperceptible ripples in the upper atmosphere? Could its gravitational field interact faintly with ionospheric density? Such effects, if detectable, would be vanishingly small, but the attempt to measure them reveals the hunger for every scrap of knowledge this encounter might yield. And the timing is exquisite. In 2029, humanity will be deep into a new age of exploration. Mars missions, lunar bases, and deep space observatories will be active. Apophis may be observed not just from Earth, but from spacecraft stationed around the solar system, offering multiple vantage points on the flyby. It will be a global moment of scientific synergy. The encounter is not only a spectacle, it is also a turning point for planetary defense. Every observation will enrich our models, sharpen our understanding of orbital mechanics, and refine our ability to respond to threats. The next potentially hazardous asteroid we discover may resemble Apophis in size, shape, or structure. When that day comes, the lessons of 2029 will be the blueprint for action, and humanity will not limit itself to watching from afar. In a bold move, NASA has reassigned its OSIRIS-REx mission, which successfully sampled asteroid Bennu to a new role. The spacecraft, renamed OSIRIS-APEX, Apophis Explorer, is set to rendezvous with Apophis shortly after its close pass. There, it will map the surface, study the aftermath of tidal stresses, and observe changes that Earth's gravity may trigger. For the first time, we will have a spacecraft on hand to witness the immediate consequences of a planetary close approach. So why does 2029 matter if no impact is coming? Because it transforms Apophis from an object of fear into an astronomical gift. It is a reminder of our vulnerability, but also of our capacity for foresight and preparation. It is a test of science, technology, and communication, playing out not in the abstract but in the skies above us. When that night comes, people will gather in cities and villages, in deserts and observatories, to watch a moving star that should not be there. They will witness a relic of the solar system's birth sweep past, close enough to alter its destiny, and they will know, perhaps for the first time in a visceral way, that we are part of a living, dynamic cosmos where risk and wonder are inseparable. The 13th of April 2029 will not be remembered as a day of doom, but as a turning point, the night Earth's people looked up and saw not a threat, but a future, a civilization capable of watching the skies, measuring the risks, and learning from them before it is too late. Part 5. The Post-Flyby Rendezvous. Sometimes the universe aligns with uncanny timing. As if by design, the most dangerous asteroid scare of the modern era will not only pass us harmlessly in 2029, but it will do so under the watchful gaze of a spacecraft already tested in battle. A machine with scars of dust from another world, refitted, renamed, and repurposed to meet this moment. That machine is OSIRIS-APEX. Its story begins not with Apophis, but with Bennu, originally christened OSIRIS-REx Origins, spectral interpretation, resource identification, and security regolith explorer. The spacecraft spent 2 years in close embrace with the 500-meter asteroid. It mapped every boulder, every slope, every vein of dust. In October 2020, it dipped down, kissed the surface with its robotic arm, and captured samples of ancient material. Then, after a return flight across millions of kilometers, it released a capsule that parachuted safely to Earth in September 2023, carrying pieces of Bennu older than our planet itself. Most spacecraft would retire at that point, their mission complete. OSIRIS-REx, however, had fuel in its tanks, functioning instruments, and a record of resilience. NASA saw opportunity. Instead of letting a proven explorer fade into silence, they extended its life and redirected its path. Its new target, the Serpent of Chaos itself, Apophis, its new name, Osiris, Apex, Apophis Explorer. The plan is audacious. Osiris Apex will intercept Apophis in June 2029, just 2 months after the asteroid's record-breaking flyby of Earth. That timing is crucial, close enough to observe whatever changes Earth's gravity inflicted, but late enough to allow the spacecraft to approach safely and stabilize operations. Once it arrives, Osiris Apex will remain with Apophis for 18 months, conducting the most detailed, prolonged study of any asteroid in human history. The mission's science objectives read like a planetary defense checklist. First, measure how Earth altered Apophis's orbit and rotation. Ground-based telescopes can track the broad strokes, but only a spacecraft can capture the fine detail, the precise shift in spin rate, the exact wobble in orientation, the subtle adjustment in trajectory. These measurements will validate the models we rely on when simulating how an asteroid might respond to deliberate deflection. Second, document surface changes. The OCAM's imaging system, capable of resolving features just centimeters across, will scan for landslides, boulder shifts, or newly exposed patches of fresh rock. If Earth's tidal forces triggered avalanches across Apophis's rubble-pile surface, OCAMs will see them. The OTES spectrometer will map heat across the asteroid, detecting areas where darker, untouched material has emerged. Such exposures are like time machines, revealing the interior composition before it was weathered by cosmic radiation. And third, conduct an experiment never attempted before, a thruster disturbance maneuver. Osiris Apex will descend to within 25 meters of Apophis's surface and fire its engines, deliberately lofting dust and pebbles into space. This is not a sample collection attempt. The spacecraft no longer carries its TAGSAM arm, but a calculated attempt to probe the regolith. How tightly is the surface bound? Does dust cling or fly free? Does the rubble cascade like sand or cling together like clay? The answers will help engineers design deflection missions, where the transfer of momentum depends heavily on surface properties. This maneuver is bold, risky, and deeply symbolic. It shows how far we've come, from treating Apophis as a looming apocalypse to daring to reach down and stir its dust. But the encounter is no simple task. By the time Osiris Apex reaches Apophis, the asteroid may not be the same world we thought we knew. Earth's gravity could alter its rotation period, shift its pole orientation, or even rearrange its surface topography. Navigating such a body requires constant recalibration. Mission planners must adapt their flight dynamics in real time, building new maps from Osiris, Apex's initial images, updating hazard models daily, maneuvering with a precision measured in meters. The engineering challenge alone is historic. By 2029, the spacecraft will have been operating for over a decade, twice its planned lifespan. Its longevity will prove that asteroid missions need not be single-target ventures. Instead, one well-built explorer can visit multiple worlds across years, creating a model for the future. Rovers of the void, dispatched to wherever the next threat emerges. And the scientific payoff? Immense. By comparing pre-flyby Earth-based observations with Osiris, Apex's post-flyby data, we will gain the first ground truth measurements of how a massive gravitational encounter reshapes a rubble pile asteroid. We will see, with certainty, whether our models of tidal stress and orbital mechanics align with reality. For planetary defense, this is pure gold. If we ever need to nudge an asteroid off course with a kinetic impactor or a gravitational tractor, we must know how rubble piles behave when subjected to external forces. Apophis provides the natural experiment, OSIRIS Apex, the instruments. But the mission is more than science. It is also a test of cooperation. Radar observatories in California and Puerto Rico, optical telescopes across Europe and Asia, infrared surveys from orbit all will coordinate with OSIRIS Apex, merging data into the most complete portrait of a single asteroid ever assembled. This synthesis will serve as a template for how humanity responds when the next true threat is discovered. The timeline itself is elegant. The spacecraft arrives in June 2029, after Apophis has moved safely beyond Earth's gravitational grasp. It will orbit, map, and analyze through 2030, observing the asteroid under shifting sunlight and from multiple geometries. It will watch Apophis spin, tumble, and reveal its secrets, all while streaming back data that may define the next generation of planetary defense. The thruster disturbance test stands out as the most daring innovation. If OSIRIS Apex's jets can loft material into space, instruments can analyze the grain sizes, binding forces, and composition of debris. This miniature artificial impact provides a scaled-down simulation of what a real deflection attempt might achieve. If the regolith proves fragile and loosely bound, then kinetic impactors may achieve more momentum transfer than expected, a valuable insight for future missions. Perhaps the greatest significance of OSIRIS Apex is philosophical. It shows that missions need not end when samples are returned or when primary objectives are complete. A spacecraft can be reborn, extended, redirected toward new questions. Science and defense can merge. One mission studying planetary formation at Bennu, the same mission safeguarding planetary survival at Apophis. Public interest will follow. In April 2029, billions will watch Apophis streak past Earth. 2 months later, OSIRIS Apex will continue the story, moving from spectacle to science, from headlines to hard data. Students who watch the flyby may later analyze OSIRIS Apex images in classrooms. The asteroid that once threatened doom will become a touchstone of education, communication, and preparedness. The data will echo for decades. Today, impact risk assessments rely on statistical distributions of asteroid properties, many inferred from limited observations. OSIRIS Apex will provide real, detailed measurements of how a rubble pile asteroid actually behaves when stressed. Those numbers will refine models, sharpen predictions, and improve humanity's ability to evaluate new threats as they appear on our radar. Apophis's transformation from chaos serpent to laboratory subject illustrates the arc of planetary defense itself. At first, uncertainty breeds fear, a 2.7% chance of impact. Then, measurement brings clarity. No collision in 2029, nor for a century beyond. Finally, vigilance turns fear into opportunity. A spacecraft rendezvous, a mission extended, a civilization learning not only how to survive, but how to grow wiser. In the end, OSIRIS Apex is more than a spacecraft. It is a symbol of how we must approach the cosmos. With caution, yes, but also with persistence. With awe, but also with calculation. With the humility to fear the rocks that share our orbit, and the ambition to chase them down. Because the story of Apophis does not end in 2029. It begins there, And Osiris Apex will be our witness, our envoy, our guarantee that the lessons of that night are captured, studied, and carried forward into the uncertain centuries ahead. Part 6. How we got the risk wrong, then right. On the 27th of December 2004, at NASA's Jet Propulsion Laboratory in Pasadena, planetary scientist Stephen Chesley sat staring at numbers that refused to go away. He had rerun the calculations again and again, hoping for a mistake. There wasn't one. Based on just 74 positional measurements spanning 64 days, the orbital solution for asteroid 2004 MN4, soon to be named Apophis, suggested something extraordinary: a 2.7% chance of striking Earth on the 13th of April 2029. To most people, 2.7% sounds negligible, but in the language of asteroid dynamics, it was astronomical. Consider the comparison. Your lifetime odds of being struck by lightning are about 0.007%, or 1 in 15,000. At that moment in 2004, Apophis looked to be more than 300 times more likely to hit Earth than you are to be struck by lightning in your entire life. That number earned Apophis a place in history. On the Torino Impact Hazard Scale, a system devised by MIT's Richard Binzel and adopted at a 1999 conference in Turin, Italy, Apophis scored a level 4. The scale runs from 0 to 10, where 0 means no risk and 10 means certain collision, global catastrophe. Almost every newly discovered asteroid quickly drops to level 0 as more data refines its orbit. For Apophis to sit at level 4 was unprecedented. Level 4 means a close encounter meriting attention by astronomers, with a non-negligible chance of regional devastation. The media seized on it. Headlines blared about an asteroid with Earth's name on it. Impact in 2029 became the question of the hour. But in the noise, one crucial nuance was lost. That 2.7% was not a prediction of doom, it was a measurement of uncertainty. Why? Because early orbital determinations are fragile things. Imagine watching someone throw a baseball but seeing only the first fraction of its arc. You'd be wildly uncertain about where it would land. Now stretch that out. The throw happened millions of years ago, and the catch will occur decades in the future. Each observation of an asteroid, each tiny dot measured against the background stars, tightens the picture. But with only a few dozen data points, the uncertainty ellipse is enormous. That was Apophis in late 2004. Those initial 74 observations, covering just 2 months, could not yet pin down the orbit with precision. Small errors in measurement ballooned into large uncertainties in where the asteroid might be decades later. That 2.7% impact chance was not a statement that Apophis was likely to hit Earth. It was a statement that, given the limited data, astronomers could not yet rule it out. Adding to the drama was the concept of gravitational keyholes. During Apophis's close approach in 2029, Earth's gravity would bend its trajectory. If the asteroid passed through a narrow region of space, sometimes no wider than a few hundred meters, our planet's gravity could deflect it onto a future collision course. For Apophis, the keyhole that mattered was the one leading to a possible 2036 impact. It was estimated to be about 600 meters wide, smaller than many city blocks. Yet given the uncertainties in Apophis's path, astronomers could not rule out the possibility of it threading that cosmic needle. The problem wasn't the math. The problem was communication. News reports trumpeted the 2.7% figure, often stripped of its context. To the public, it sounded like a prediction of disaster. To scientists, it was simply a reflection of incomplete knowledge. Professionals understood that more observations would almost certainly shrink the risk to 0. But until those measurements arrived, the possibility lingered. And so, for the first time, the world mounted a coordinated global campaign to track a single asteroid. Observatories on every continent pointed their telescopes toward Apophis whenever it was visible. Radar facilities like Arecibo in Puerto Rico and Goldstone in California bounced signals off the asteroid, measuring its distance and speed to within meters. Space-based observatories provided astrometric data free of atmospheric distortion. Every new data point narrowed the error bars. The breakthrough came when NASA's Don Yeomans and his team turned to archival sky surveys. Hidden in images taken before Apophis's official discovery were precovery detections, tiny points of light that, when identified, doubled the observational arc. With positions dating back to March 2004, astronomers could now extend their calculations with far greater accuracy. The results were decisive. By late 2005, the impact probability for 2029 had collapsed to virtually zero. Apophis would indeed pass closer than our geostationary satellites, closer than anything its size in recorded history, but it would miss Earth by about 32,000 kilometers. The 2029 date was transformed from a possible doomsday into a spectacle of cosmic precision. Yet uncertainties lingered. Could Apophis still pass through the 2036 keyhole during its 2029 flyby? The possibility was low, but not yet eliminated. For years, astronomers kept Apophis under surveillance, refining its orbit, updating models, chipping away at the margins of doubt. The final piece fell into place with the Yarkovsky effect. This tiny but relentless force, the recoil from sunlight absorbed and re-radiated as heat, can slowly shift an asteroid's orbit by hundreds of meters per year. To predict Apophis's long-term trajectory with confidence, astronomers needed to measure its Yarkovsky drift. That required astrometric precision, accumulated over more than a decade. In 2021, independent teams succeeded. Apophis was drifting at about 170 meters per year in its semi-major axis. That subtle push, compounded over decades, was enough to move it away from the 2036 keyhole. With the Yarkovsky effect measured and modeled, astronomers could declare with confidence Apophis posed no impact threat for at least the next 100 years. It was one of the most thoroughly validated negative predictions in the history of planetary science. This progression from 2.7% alarm to 0% certainty illustrates how planetary defense is meant to work. Early observations produce high uncertainty and seemingly high probabilities. Continuous tracking shrinks those uncertainties. Probabilities fall, threats vanish. What begins as panic resolves into clarity. The Apophis episode also rewrote the playbook for risk communication. Initial probabilities must be presented as provisional, not definitive. Media must emphasize uncertainty, not strip it away. The public must understand that most asteroid scares dissolve under the weight of better data, but only if the world invests in the infrastructure to collect it. International coordination proved equally critical. NASA's Planetary Defense Coordination Office, ESA's Space Situational Awareness Program, and dozens of observatories worldwide contributed. The template they built distributed observations, pooled data, collaborative analysis now stands ready for future threats. Most importantly, Apophis taught us the difference between statistical uncertainty and existential danger. That initial 2.7% was not doom, but doubt. The data couldn't yet rule out catastrophe, so the risk calculation had to reflect that ignorance. The difference between possible and probable is everything. In hindsight, Apophis became a case study in science functioning exactly as intended. Early alarms spurred action, observations accumulated, uncertainties collapsed. The threat evaporated. By the time the 13th of April 2029 arrives, Apophis will no longer be a serpent of chaos but a scientific spectacle, a naked-eye asteroid flyby remembered not for what might have been, but for what we learned. And yet, one sobering truth remains. This time, the numbers shrank. What if they hadn't? What if additional data had confirmed, not eliminated, the risk? The hypothetical impact of an Apophis-sized asteroid regional devastation, millions dead, economies shattered reminds us why planetary defense matters. It reminds us why interstellar visitors like 3I Atlas, beautiful though they are irrelevant to the dangers that keep experts awake at night. Because the true threats are not rare tourists. They are the neighbors whose orbits we are still learning to map, the rubble piles and rocky masses drifting quietly through our shared solar home. Part 7. What if an Apophis-class rock hit Earth? Let us imagine, just for a moment, that the story of Apophis had unfolded differently, that instead of the reassuring certainty we hold today, the calculations had confirmed our worst fears. The 13th of April 2029, a date circled in red, not as a celestial spectacle, but as the day civilization might face its most violent test. What approaches is not science fiction, but a rock 340 meters across, a mass of silicate stone laced with nickel iron, rushing toward Earth at 25 kilometers per second. The numbers alone stagger the mind. Half a gigaton of energy, equivalent to 10 Tsar bombers, the Soviet superweapon that once defined the upper bound of human-made destruction. But energy figures are abstractions. To understand what such a collision means, we must turn those numbers into landscapes of fire, shock, and collapse. If Apophis were to strike land, the aftermath would be apocalyptic on a regional scale. The impact crater would span 4 to 5 kilometers in diameter, gouged into the crust with explosive force that vaporized everything within a zone of several kilometers. Temperatures would rise for a fleeting instant to match those of the solar photosphere, annihilating life and matter indiscriminately. A fireball some 15 kilometers across would roll outward, igniting forests, cities, and fields. Within that radius, survival would be impossible. Beyond it, the shockwave would still scythe across the landscape, flattening buildings, hurling debris, and killing nearly everything within 50 kilometers. The Earth itself would ring from the seismic waves, tremors propagating across continents, registering on seismographs oceans away. Above, dust and pulverized rock would billow into the stratosphere, cloaking skies, blotting sunlight, and setting the stage for agricultural collapse. The oceanic alternative is no reprieve. At tens of kilometers per second, water becomes concrete. A strike into the Pacific or Atlantic would vaporize millions of tons in an instant, unleashing a steam plume visible from orbit and launching tsunamis that would not respect coastlines or nations. Waves 10 to 20 meters high could race across thousands of kilometers, reaching shores with barely any warning. History offers sobering context. The 2004 Indian Ocean tsunami, born of a magnitude 9, one quake, killed over 230,000 people across 14 countries. An Apophis-generated wave train would be larger still, its impact multiplied by modern coastal populations and infrastructure clustered along low-lying shores. The scale of devastation grows clearer when placed beside smaller, yet still destructive events. In 2013, the Chelyabinsk meteor, a rock only 20 meters across 60 times smaller than Apophis by volume, exploded high above Russia, shattering windows and injuring over 1,500 people. If something so small could do so much damage, what then of a body 340 meters wide? We move from shattered glass to shattered nations, from 1,000 injuries to millions of deaths, from temporary shock to the potential unraveling of regional civilization. Global consequences follow inevitably, even if not extinction level like the Chicxulub impact that ended the dinosaurs. An Apophis-class collision would trigger climate disruption measurable on a planetary scale. A veil of dust and aerosols would cool temperatures by 1 or 2 degrees Celsius for years. That may sound modest, but history reminds us of the fragility of agriculture to such shifts. A few degrees in the wrong direction at the wrong time can collapse harvests, disrupt supply chains, and push billions into food insecurity. In an interconnected world, the ripple effects would extend far beyond the impact zone. Supply chains would fracture, markets would crash, economies built on just-in-time logistics would stumble into cascading failure. The 2011 Tohoku earthquake and tsunami, while devastating locally, reverberated through global industries for months. An asteroid strike would dwarf that disruption, stretching the shock across years and continents. Yet the material consequences tell only half the story. The psychological scar of such an event might linger longer than the dust. Unlike hurricanes or earthquakes, which belong to familiar categories of natural disaster, an asteroid impact carries with it the existential weight of cosmic indifference. To watch one's skies burn with fire from the heavens would reshape humanity's collective self-image, reminding us that our planet remains fragile, vulnerable, exposed to forces vast and impersonal. Survivors would rebuild in the shadow of that knowledge, and generations would inherit a consciousness of planetary fragility unlike anything before. Emergency response systems, tuned to terrestrial disasters, would strain under the impossible complexity of such an event. Evacuations on a scale of millions would be required, not for days but for decades. As entire regions became uninhabitable, populations would need permanent relocation. Borders would bend under the pressure of refugees. Resources would collapse under demand. No single nation could bear the weight. International coordination, already tenuous in lesser crises, would become a prerequisite for survival. Relief agencies, governments, militaries, and scientists would need to act in unison, not out of charity but necessity. The financial cost is almost beyond imagination. The Tohoku disaster caused $200 billion in damage. Hurricane Katrina, $125 billion. Apophis could unleash over $1 trillion in immediate destruction, with the true toll economic disruption, food crises, resettlement stretching far beyond that figure. In such calculations lies the rationale for planetary defense as policy, not speculation. The threat may be low in probability, but in consequence it towers over most hazards humanity faces. Risk analysts call this the high-consequence, low-probability scenario, the catastrophe we cannot dismiss, precisely because its possibility, however remote, carries stakes too large to ignore. And here, the distinction between 3I, Atlas, and Apophis comes into stark relief. Atlas, though exotic, will never come near Earth, its hyperbolic path carrying it out of the solar system forever. Its danger is zero. Apophis, by contrast, was real enough to mobilize a generation of planetary defense infrastructure. It crosses Earth's orbit. It raised probabilities, however briefly, to the level where humanity had to look seriously at the prospect of impact. And even though new observations ruled out disaster this time, the fact remains. Objects like Apophis exist, and sooner or later one will not miss. The thought experiment, then, is more than imagination. It is rehearsal. To picture Apophis striking Earth is to understand why planetary defense has risen from science fiction to policy imperative. To weigh probabilities against consequences is to see why we cannot afford complacency. The visitor from another star captures our wonder. The neighbor crossing our orbit demands our vigilance. Even though new measurements have eliminated its threat for the next century, Apophis remains in the roster of the potentially hazardous asteroids, a population of objects whose orbits carry them close enough to matter and whose sizes make them dangerous if they ever do hit. The distinction between what is spectacular and what is dangerous has never been clearer. On one side stands 3I Atlas, the interstellar comet capturing headlines with its rarity and exotic origins. On the other stands Apophis, an utterly ordinary asteroid by composition, yet a case study in why humanity needs a planetary defense program in the first place. One is a beautiful curiosity. The other is a wake-up call. Sometimes the most important lesson comes not from what threatens us, but from what doesn't. Atlas and Apophis embody opposite ends of the hazard spectrum. One dazzling but harmless, the other drab yet consequential. Understanding the difference requires stripping away the headlines and focusing on the cold mathematics of orbital mechanics and risk assessment. Start with the numbers. 3I Atlas will reach its closest approach to Earth on the 19th of December 2025, at a distance of 1.797 astronomical units, about 268 million kilometers. That is a chasm so vast you could line up the moon inside that gap nearly 700 times. Its hyperbolic trajectory never intersects Earth's orbital lane. By definition, Atlas is irrelevant to planetary defense. Apophis, by contrast, will pass within 32,000 kilometers of Earth's surface on the 13th of April 2029. That is inside the orbit of our geostationary communications satellites at 35,786 kilometers. Apophis will literally thread the gap between our planet and critical infrastructure we ourselves have placed in space. The comparison is stark. Atlas misses us by a factor of 8,000 compared to Apophis's closest approach. And yet, which object has dominated public imagination? Which has filled news feeds with artists' impressions and speculative headlines? The comet, the harmless one. The reason lies deep in psychology. Rarity captivates us. Atlas is only the third confirmed interstellar visitor ever observed, following Oumuamua and Borisov. The alien traveler narrative writes itself, a visitor from another star with hints of mystery, perhaps even speculation about extraterrestrial origins. Our brains are wired to prioritize the unusual, the exotic. Meanwhile, Apophis follows an ordinary near-Earth asteroid orbit, made of silicate rock and nickel-iron metal, the most common stuff in the inner solar system. By every measure except the one that matters, proximity Apophis is unremarkable, and yet Apophis briefly carried the highest calculated impact probability of any asteroid ever discovered. Its early numbers, a 2.7% chance of impact, pushed it to level 4 on the Torino scale, the first real object to ever reach that mark. For planetary defense professionals, it was an earthquake. Observatories scrambled, governments noticed, protocols were drafted. NASA's Planetary Defense Coordination Office did not exist in 2004 when Apophis was first detected, but the scare it triggered helped justify its creation. The European Space Agency expanded its Space Situational Awareness program, partly because of the lessons Apophis forced the world to learn. No such institutional ripples accompany Atlas, nor should they. The comet requires no special monitoring beyond scientific curiosity. It poses no threat, offers no warning, and provides no lessons about how to respond when danger is real. This is the paradox of public education. Atlas offers a dazzling hook to draw attention, but it risks overshadowing the mundane reality of genuine threats. The opportunity is to use the comet's celebrity as a doorway capturing imagination. then redirecting it toward the quiet, patient work of planetary defense. The danger is to let spectacle consume substance, leaving the public enchanted by irrelevancies while oblivious to the real stakes. Consider how the stories are told. A 3-1 Atlas news cycle begins with breathless announcements. Alien visitor discovered. Images show its coma, its growing tail, the romance of interstellar drift. Only in paragraph 7 or 8 does the disclaimer appear. No threat to Earth. Most readers never see it. Near-Earth asteroids are different. Unless they carry an immediate chance of collision, they rarely break into the news. Their cataloging continues quietly. In professional journals and technical bulletins, few laypeople ever read. Today, we know of more than 34,000 NEAs. Ask the average person to name one besides Apophis, and you will likely get silence. This imbalance distorts public perception. People grow familiar with harmless curiosities, while the very real threats remain obscure. And when the next Apophis-class asteroid is discovered, and statistics guarantee more are waiting, public confusion about relative risk could slow the policy responses that matter. The asymmetry extends beyond publicity into the very mechanics of risk assessment. 3. Atlas generated thousands of articles, countless posts, endless chatter all about an object with zero probability of harm. Meanwhile, teams of astronomers spend decades tracking NEAs, refining orbits, monitoring perturbations. Their work rarely leaves specialized circles, even though it represents the only realistic shield humanity has against future impacts. To their credit, space agencies have learned from Apophis. When Atlas was discovered, NASA and ESA were clear and consistent: no threat. Every official release emphasized the distance, the certainty, the harmlessness. These were not cautious hedges. They were mathematical facts. The same clarity has since been applied to Apophis itself. After years of refinement, the agencies now state with equal certainty: Earth is safe from Apophis for at least a century. This progression from uncertainty to confidence is how planetary defense is supposed to function. Early alarms mobilize effort, observations accumulate, probabilities shrink, confidence grows, threats vanish. What remains is the infrastructure, the surveys, telescopes, data pipelines, and communication protocols built to handle the next case. Atlas and Apophis thus symbolize opposite categories in the taxonomy of space hazards. Atlas belongs to the class we do not need to fear, rare interstellar tourists that pass once and never return. Apophis belongs to the class we must monitor relentlessly, near-Earth asteroids, their orbits evolving under the tug of planets and the whisper of sunlight, their paths occasionally bringing them too close for comfort. The distinction matters for budgets, telescope time, and international policy. Every dollar spent chasing harmless fireworks in the sky is a dollar not spent cataloging NEAs. Every hour of telescope, tracking an interstellar curiosity, is an hour not spent tightening the uncertainty ellipses of asteroids that actually might hit us. This is not an argument against studying Atlas or its kin. The comet holds genuine scientific treasure, clues to the chemistry of distant star systems, insights into how comets survive interstellar journeys, context for planetary formation. These are worthy pursuits, but they are not planetary defense. The 2029 flyby of Apophis will provide something Atlas cannot: actionable knowledge. It will transform fear into data, uncertainty into understanding. Ground-based telescopes, radar networks, and the OSIRIS-APEX spacecraft will capture every nuance of how a rubble pile asteroid responds to tidal stress. Those measurements will feed directly into deflection models, the very simulations that might one day determine whether Earth survives a future impact. And that is the heart of the lesson. Danger is not defined by spectacle. It is defined by the equation of proximity times size times probability. Atlas is exotic but irrelevant. Apophis is ordinary but instructive. The first teaches us about other worlds. The second teaches us how to defend our own. In the long arc of civilization, both matter, but only one matters for survival. Part 8. The 2029 show, What We'll Measure. On the 13th of April 2029, the sky will host the most intensively studied asteroid encounter in human history. That night, Apophis, a body once feared as a possible doomsday rock, will pass closer than our geostationary satellites, and every major observatory on Earth will turn its gaze toward it. The event is more than spectacle. It is a carefully prepared experiment. Astronomers have been building a baseline portrait of Apophis for years. During its 2021 apparition, telescopes mapped its shape, rotation rate, surface brightness, and thermal signature. Now, with Earth's gravity preparing to tug at this elongated asteroid, scientists will finally be able to compare before and after with unprecedented precision, measuring exactly how a close planetary encounter reshapes a celestial body. Radar will provide the sharpest eyes. The Goldstone Solar System radar in California and the Green Bank Telescope in West Virginia can resolve Apophis at meter-level detail, producing three-dimensional images detailed enough to pick out individual boulders. If Earth's tidal forces shuffle surface material, trigger landslides, or expose brighter subsurface rock, radar will reveal those changes instantly. Photometry will track its spin. Apophis currently rotates once every 36 hours, a slow tumble. But Earth's pull will likely alter that rhythm, speeding it up or slowing it down depending on orientation. By recording subtle flickers in brightness as different faces rotate into sunlight, astronomers will know whether the asteroid's heartbeat has shifted. Professional observatories will lead this effort, but thousands of amateur astronomers across the globe will join in as well, coordinated through long-prepared campaigns that treat the encounter as both science and civic engagement. Infrared observations will add another layer of information, searching for heat signatures that betray freshly exposed surfaces. Over millions of years, asteroid surfaces darken and redden under bombardment from solar wind and micrometeorites. If tidal stress tears away that weathered skin, the infrared glow will reveal younger, brighter rock underneath. NASA's NEOWISE mission already provides thermal benchmarks, and 2029 will test whether Earth's gravity can reset parts of an asteroid's surface clock. Spectroscopy will probe even deeper, breaking light into mineral fingerprints. If fresh material is exposed, the balance of silicates, metals, and carbon compounds may shift subtly, offering clues about Apophis's composition that were previously hidden. Underlying all these efforts is a central scientific question: what lies inside? Is Apophis a coherent block, fractured but strong, or is it a rubble pile, a fragile heap of boulders held together only by gravity's whisper? The encounter could tell us. Earth's pull at closest approach will exert forces about 50 times stronger than the asteroid's own gravity. A solid object may shrug off the stress with only minor changes, but a rubble pile could rearrange dramatically, slumping, cracking, or reshaping in real time. The asteroid's elongated form complicates the prediction further. Depending on its orientation as it swings past Earth, tidal forces could stretch it even more or tug it toward a rounder profile. At 21:46 UTC on the 13th of April, the instant of closest approach, the drama will peak, and instruments worldwide will be trained to capture every consequence. Coordinating such a campaign demands near-military precision. As Earth rotates, different continents will inherit the view, and observatories must hand off the baton seamlessly to maintain continuous coverage. Real-time data sharing will allow scientists to adjust as events unfold, while pre-planned observation sequences will ensure no surprises are missed. Light from Apophis will take only 1/10 of a second to reach Earth during closest approach, fast enough for near real-time observations, but not instantaneous, so observers will need to be ready for changes that come suddenly and pass quickly. The 2029 encounter is more than a once-in-a-lifetime spectacle. It is rehearsal for the future. Every radar ping, every thermal map, every flicker of brightness will provide ground truth for planetary defense. The data will refine models of asteroid structure and behavior, validate deflection simulations, and inform the strategies that could one day save us when the next threatening object does not pass harmlessly by. For the public, Apophis will be a visible star racing across the night sky, a reminder of both our vulnerability and our vigilance. For scientists, it will be the most precise natural experiment in asteroid mechanics ever attempted, an event that transforms fear into knowledge and spectacle into preparation. On the 13th of April 2029, we will not only witness history, we will measure it, record it, and learn from it. Knowing that the next time the numbers do not shrink to zero, we must be ready to act. The computer models that underpin our understanding of asteroid structure and behavior remain, at their core, acts of educated imagination. They rely on assumptions about material strength, internal cohesion, and how fractured rock responds to external forces. For years, planetary defense has been a discipline of simulations more than experiments, a science of extrapolation. In 2029, that changes. When Apophis skims past Earth, it will not only offer a spectacle for the eye, but a crucible for our theories. For the first time, scientists will be able to test models against reality, watching a sizable asteroid undergo measurable stress as our planet's gravity stretches, squeezes, and reshapes it in real time. The implications extend far beyond curiosity. If we can see how Apophis responds to tidal forces, we can refine predictions about how other asteroids might respond to deliberate deflection attempts, whether by kinetic impactors, gravitational tractors, or technologies yet unimagined. If Apophis proves tougher than expected, our strategies may need to change. If looser, more fragile, the lessons will be just as profound. But the 2029 campaign is more than science. It is rehearsal. Every element of the international observation effort, the coordination across continents, the rapid sharing of data, the comprehensive suite of instruments trained on a single object, is practice for the day when the stakes are no longer academic. Apophis, once an existential threat, has become something stranger, a test case that marks the transformation of planetary defense itself, from reactive panic into proactive strategy. When it was first discovered in 2004, no coherent planetary defense infrastructure existed. NASA tracked asteroids, yes, but without a central office devoted to the problem of impact hazard. The European Space Agency conducted research, but with no dedicated mandate for planetary defense. The global community had no established protocols for coordination, no authoritative body to weigh probabilities and declare risks. The Apophis scare altered that landscape. By 2006, NASA had established the Near-Earth Object Observations Program, the first institutional recognition that cataloging threats could not remain an ad hoc pursuit. Its mandate included not only discovering asteroids, but refining their orbits with the precision needed to evaluate impact scenarios. The European Space Agency followed with its Space Situational Awareness Program, later rebranded Space Safety and Security, broadening its scope from debris and solar hazards to include the asteroid problem directly. The Apophis wake-up call forced a subtle but profound shift. Planetary defense became not just astronomy, but policy. Still, institutions alone were not enough. Apophis revealed that technical readiness lagged far behind our ability to recognize threats. How do you deflect a mountain of rock and metal? To design a solution, you must know its density, its porosity, its internal cohesion, its spin, its thermal inertia. Without those parameters, any deflection attempt is guesswork. The first true experiment arrived with DART, the Double Asteroid Redirection Test. Launched in 2021, its mission was audaciously simple: hurl a spacecraft at high velocity into the small moonlet Dimorphos, which orbits the larger asteroid Didymos, and measure what happened next. On the 26th of September 2022, the impact occurred. Astronomers watched Dimorphos's orbital period shrink by 32 minutes, more than 3 times the minimum needed to declare success. The momentum enhancement factor, known as beta, reached about 3.6. The implication was extraordinary. Debris blasted off the asteroid's surface provided additional thrust, multiplying the effect of the impact itself. For the first time, humanity had proof that kinetic impactors could work. A theoretical technique had crossed into engineering reality. But DART was only half the story. The second half, ESA's Hera mission, launched in 2024 and bound for Didymos, will arrive in 2026 to conduct a forensic examination of the impact crater, the debris field, and the structural response of Dimorphos. Together, DART and Hera form a template, an active deflection test followed by close-range reconnaissance to validate models. It is the kind of two-stage approach that will be essential if a real asteroid someday threatens Earth. The success of DART reverberates directly into the Apophis encounter. When Earth's gravity tugs at Apophis, the asteroid will effectively become a natural analog of the DART experiment, an external force altering its trajectory, spin, and possibly surface structure. What we measure in 2029 will provide calibration points that refine the very models DART began to validate. Planetary defense, once theoretical, will become empirical. Since Apophis's discovery, the institutional scaffolding of defense has grown steadily. In 2016, NASA consolidated its efforts under the Planetary Defense Coordination Office, the focal point for all American asteroid detection, risk assessment, and mitigation planning. The PDCO coordinates with international partners and serves as the official voice of authority when new threats are discovered. Globally, the United Nations stepped in to formalize cooperation. The International Asteroid Warning Network, IAWN, now provides a platform for sharing discoveries and hazard updates, while the Space Mission Planning Advisory Group, SMAG, develops guidelines for response missions. These structures emerged from hard lessons. The chaotic first years of Apophis analysis, when conflicting probability estimates sowed confusion, underscored the need for unified communication and standardized methods. Today, when NASA or ESA makes a pronouncement about an asteroid, that authority rests on a globally coordinated backbone. The technological infrastructure has grown just as rapidly. In the early 2010s, near-Earth object discovery relied heavily on surveys like Linear and NEAT. Today, far more sophisticated systems operate. Atlas, the asteroid terrestrial, Impact Last Alert System, and the Zwicky Transient Facility, scanning the skies nightly for moving points of light. They discover thousands of new near-Earth objects each year, filling in the census that once seemed impossibly incomplete. Yet gaps remain. Many dangerous asteroids lurk undetected, especially those smaller than a kilometer but large enough to devastate a region or nation. The next leap comes from space. NEO-Surveyor, slated for launch no earlier than 2027, is a dedicated infrared telescope designed to hunt the dark asteroids that optical surveys miss. Its vantage above Earth's atmosphere and sensitivity to heat signatures should accelerate discovery of the elusive 100 to 500-meter objects, the city killers. Meanwhile, the Vera C. Rubin Observatory in Chile, beginning operations in 2025, will conduct the legacy survey of space and time, producing an unprecedented decade-long movie of the sky that will catch countless new asteroids in motion. All of these efforts trace their lineage back to Apophis. Without that initial scare, planetary defense might have remained a peripheral topic, half science fiction, half science. Instead, the world was forced to confront the uncomfortable truth. The sky can kill us, and the only defense is preparation. The 2029 flyby, transformed from nightmare into natural experiment, closes one chapter and opens another. It is not just the validation of models or the refinement of deflection strategies. It is the demonstration that humanity can learn from fear, can build institutions from panic, can turn uncertainty into strategy. Apophis, once the serpent of chaos, has become a teacher. It reminds us that survival is not guaranteed, that cosmic hazards remain indifferent to our confidence, but also that vigilance and cooperation can bend the arc of danger into an opportunity. And in 2029, as instruments across Earth and in space converge on its passing form, Apophis will deliver its final lesson that planetary defense is no longer theoretical, no longer optional, but the quiet, steady craft of ensuring the next rock does not catch us unprepared. The Vera C. Rubin Observatory, formerly known as LSST, the Legacy Survey of Space and Time, represents one of the most transformative instruments in the history of planetary defense. With its enormous field of view, its rapid imaging cadence, and its deep sensitivity, Rubin will capture the sky in sweeping time-lapse. Every few nights, it will return to the same patches of stars, tracing the faint wanderings of asteroids against the background. By doing this relentlessly for a decade, it could discover hundreds of thousands of new near-Earth objects and refine the orbits of those already known. It is astronomy turned into cinema, each frame a record of movement, each sequence a revelation of trajectories that may one day intersect with our own. Yet technology alone is not the end of the story. Perhaps the most important development since the Apophis scare has been the recognition that planetary defense is not just an engineering problem, it is a political, legal, and social one. To deflect an asteroid, humanity needs more than rockets. It needs authority, the legitimacy to decide who acts, when, and with what force. It needs funding, sustained not by fear but by policy. And it needs cooperation across borders, because a rock falling from the sky recognizes no nation. Apophis revealed this gap with startling clarity. In late 2004, when the probability of impact stood at 2.7%, congressional hearings were convened. NASA scrambled for emergency funding. International diplomats whispered about responsibility, whose telescope had found it, whose government would be blamed if predictions proved wrong, who would take the lead if the worst were confirmed. What began as an obscure calculation in orbital mechanics spiraled into a policy crisis. Though additional observations soon ruled out disaster, the scare exposed the absence of pre-established frameworks. If another asteroid were discovered tomorrow with even a modest chance of impact, who would make the first move? Which space agency would have the right to act? And who would shoulder the blame if that action failed? Current planning rests on a comforting assumption that a genuine impact threat will be discovered years, if not decades, before the fatal date. Time, in this narrative, is our ally. Given a decade of warning, engineers can design, launch, and guide a mission to nudge the asteroid away. The DART mission, with its spectacular success at Dimorphos in 2022, validated this scenario. The kinetic impactor worked. The orbital change was measurable. With enough warning, humanity can act. But the cosmos does not always grant decades of grace. The majority of undiscovered near-Earth objects fall into the 10 to 100 meter size range. These are not planet killers, but they are city killers, capable of erasing Tokyo or Lagos or Sao Paulo in a single morning. Worse, these smaller bodies are faint, dark, and difficult to detect. They could appear with only months or even weeks of warning. Against such a timeline, today's carefully designed mitigation strategies falter. There is no fast response kinetic impactor on standby, no fleet of rockets fueled and waiting for an emergency launch. The planetary defense community is beginning to wrestle with this problem. Concepts circulate in white papers. Pre-positioned deflection systems stationed in space. Rapid response spacecraft designed to launch within weeks. Modular architectures that can be adapted on short notice. For now, these remain theoretical sketches, echoes of the urgency that Apophis once stirred. But their very existence marks progress. The evolution from panic in 2004 to DART's triumph in 2022 shows how quickly knowledge and capability can mature when fear is transmuted into infrastructure. That infrastructure is now humanity's insurance policy. We hope never to use it. We cannot afford not to have it. While interstellar comets like 3I Atlas capture headlines with their alien mystique, the work that matters is quieter. The slow accumulation of data on ordinary asteroids, the refining of orbital catalogues, the strengthening of institutions. To understand why some objects matter more than others, astronomers classify near-Earth asteroids into orbital families. The Aten group orbits mostly inside Earth's path, with semi-major axes less than 1 astronomical unit, but aphelion distances extending just beyond Earth's orbit. These asteroids spend much of their lives close to the Sun, but their elliptical sweeps cross our trajectory. The Apollo group, by contrast, is defined by orbits that cross Earth's directly, with semi-major axes greater than 1 AU and perihelion distances dipping inside Earth's orbit. These are the most dangerous, because they intersect our path twice each revolution. Apophis belongs here, as do most of the asteroids that have raised alarms in recent decades. The Amor group approaches from the outside, their perihelia between 1.017 and 1.3 AU safe for now, but unstable in the long term as planetary tugs and subtle forces nudge them inward. And then there are the elusive Atiras, orbiting entirely inside Earth's path, hiding in the glare of the sun, visible only in fleeting twilight glimpses. Within these groups, experts focus on potentially hazardous asteroids, PHAs. The definition is coldly precise: an orbit that approaches within 0.05 AU of Earth, about 7.5 million kilometers, and a size of at least 140 meters in diameter. That threshold is not arbitrary. Smaller impacts are frequent but localized. Larger ones are rare but catastrophic. At 140 meters, an asteroid carries enough kinetic energy to devastate a major metropolitan area, killing millions and triggering global aftershocks in trade, infrastructure, and psychology. Today, more than 2,000 PHAs are catalogued. Several hundred more join the list each year as surveys refine their reach. Yet this is still only a fraction of what lurks unseen. Statistical models suggest tens of thousands remain undiscovered, hidden in the sun's glare, drifting in orbits poorly aligned for ground-based detection. The story of discovery is one of accelerating awareness. In 1990, fewer than 200 NEAs were known. By 2000, The number had passed 1,000. Today, over 34,000 are catalogued, with about 3,000 added each year. The kilometer-class giants, the true extinction engines, are nearly all mapped. 90% are accounted for, and none threaten Earth in the foreseeable future. That is reassuring. But the mid-sized city killers remain the blind spot. Fewer than 40% of the 140-meter PHAs have been found. The rest are waiting in darkness. This blind spot is not just academic, it is dangerous. The Chelyabinsk meteor of 2013, a rock only 20 meters across, injured 1,500 people and caused millions in damage when it exploded in Earth's atmosphere. It was invisible until the moment it arrived, approaching from the direction of the sun where no telescope could see it. Scale that object up by a factor of 7 into the 140-meter class, and you have a regional catastrophe. Not extinction, but collapse. Millions dead, cities erased, economies convulsed. And yet such rocks are almost certainly out there, passing unnoticed, waiting for geometry and timing to align. The solution lies in looking beyond the visible. Space-based infrared telescopes can see asteroids not by their reflected light, which makes dark ones invisible, but by their heat. Every asteroid warmed by the sun glows in thermal infrared, betraying its size and location. The upcoming NEO-Surveyor mission is humanity's answer. Slated for launch late in this decade, it will dedicate itself to finding the dark, the small, the overlooked. It will hunt not the spectacular visitors, but the dangerous neighbors, the rocks that follow elliptical orbits through our shared gravitational home. And that is the paradox at the heart of planetary defense. The objects most likely to endanger us are not the exotic travelers from other stars, not the bright-tailed comets that inspire headlines. They are the mundane, the ordinary, the stones that hide in sunlight and drift invisibly through the inner solar system. The lesson of Apophis was not only that threats can be measured away, but that vigilance must be systematic, institutional, and relentless. Spectacle captures our imagination. Survival depends on what we cannot yet see. The next leap in planetary defense will come from missions like NEO-Surveyor, designed to accelerate discovery rates for potentially hazardous asteroids in the size range most likely to elude us today. These are the mid-sized objects, hundreds of meters across, that remain the largest undiscovered threat. For decades, detection technology has been steadily improving, transforming asteroid hunting from a niche pursuit into a global safety infrastructure. In the late 1992s, the linear survey dominated the field with 1-meter telescopes and basic CCDs, remarkable for their time but limited in reach. Today's instruments are larger, sharper, and far more automated. The Asteroid Terrestrial Impact Last Alert System, ATLAS, now scans the skies from Hawaii, South Africa, Chile, and Australia, giving nearly continuous global coverage. Its telescopes can detect objects as small as 20 meters in diameter just days before a potential strike, enough warning to mitigate local disasters like the Chelyabinsk event, though not to stop them. Meanwhile, the Zwicky Transient Facility, ZTF, armed with a 500-megapixel camera, sweeps wide regions of the night sky with unmatched speed, discovering thousands of asteroids each year while refining the orbits of known ones. But even these systems will look modest once the Vera C. Rubin Observatory begins operations in 2025. Its legacy survey of space and time will image the entire accessible sky twice weekly, producing a dataset deep enough to uncover hundreds of thousands of new objects and precise enough to erase much of the uncertainty that once plagued impact risk calculations. Yet discovery is only the beginning. Every new detection enters a long process of follow-up observations, the slow work of pinning down its orbit against the background stars until predictions become reliable. This can take months, even years, during which preliminary impact probabilities hover in a grey zone of uncertainty. The story of Apophis revealed how misleading those early numbers can be. Its infamous 2.7% impact probability in 2029 was never a prophecy, only a reflection of incomplete data. As more observations came in, the probability shrank to zero, but not before sparking headlines and panic. Planetary defense experts now emphasize caution in communicating early risk estimates, distinguishing clearly between provisional figures and settled predictions. At the center of this global effort stands NASA's Center for Near-Earth Object Studies, CNEOS. Its automated Sentry system continuously scans the orbits of every known near-Earth asteroid, projecting their paths decades into the future. When it detects even a sliver of non-zero probability, the system raises a flag, triggering urgent follow-up observations by telescopes worldwide. This systematic vigilance, built from the lessons of Apophis and refined through decades of surveys, has become humanity's early warning network for cosmic catastrophe. It is a sentinel that never sleeps, sifting through thousands of trajectories every day, ready to identify the next threat years before impact. For the first time in history, we can say with confidence that the sky is being watched. Part 9. Communicating Risk Without Fear. The 13th of April, 2029, will mark not only a milestone in planetary science, but also one of the greatest challenges in modern science communication. An asteroid, the size of a mountain, will pass between Earth and the geostationary satellite belt, visible to the naked eye for millions of people across Europe, Africa, and Western Asia. That fact alone sounds terrifying, and without careful messaging, it could trigger unnecessary fear. Yet the truth is both simpler and more reassuring. Apophis poses no threat, not in 2029, not for at least another century. The task for planetary defense experts, educators, and communicators is to make sure the public understands this without diluting the awe and importance of the encounter. The contradiction at the heart of this event lies in the difference between proximity and danger. Apophis will indeed come closer to Earth than any asteroid of comparable size in recorded history. At just 32,000 kilometers from the surface, it will skim inside the orbit of our geostationary satellites. In everyday human terms, that sounds perilously close. But orbital mechanics is not everyday intuition. Decades of precise observations and refinements have given astronomers absolute certainty about Apophis's path, and that path misses Earth by a comfortable margin. This isn't hedged with caveats or probabilities, it is a mathematical certainty. Communicating that certainty, in language accessible to the public, will be the foundation of the 2029 outreach effort. NASA and ESA have already learned hard lessons from the first Apophis scare in 2004. Early press coverage emphasized a 2.7% impact probability without explaining that it was really a measure of uncertainty, not of doom. Safety disclaimers were buried beneath headlines about cosmic chaos. In 2029, the messaging will be inverted. Every official communication now begins with the safety statement: Apophis will not hit Earth. Only after establishing this baseline do agencies move into the rich scientific story, the chance to observe tidal forces at work, the opportunity to refine planetary defense models, the spectacle of a visible asteroid encounter. By leading with clarity and certainty, scientists protect public trust while keeping fear at bay. Visual tools will be indispensable. Scale diagrams comparing Apophis's flyby with the Moon's orbit and the geostationary belt can make the numbers tangible. Done well, These graphics show how close, in astronomical terms, still means perfectly safe in human terms. Done poorly, they risk exaggerating danger. Striking the right balance, conveying both the rarity and the harmlessness, is the communicator's art. Amateur astronomers will also become allies in this process. Their telescopes and cameras will capture real-time footage of Apophis streaking across the sky, transforming abstract orbital diagrams into shared human experience. These grassroots campaigns, already being coordinated through the International Astronomical Union, promise to turn the encounter into a celebration of global skywatching rather than a source of dread. Social media poses the sharpest challenge. Sensational headlines thrive on half-truths. Asteroid, to pass closer than satellites, is irresistible clickbait, even without context. Planetary defense experts must therefore prepare not just to issue accurate statements, but to counter misinformation in real time. Preemptive educational campaigns will help inoculate the public against false narratives, explaining, before the memes circulate, why Apophis cannot suddenly veer off course or why satellites are not at risk, will blunt the power of fear-driven stories. The contrast with 3I Atlas, the interstellar comet that will safely pass hundreds of millions of kilometers away, also provides a teaching moment. Rarity is not the same as risk. Apophis matters because it's close, not because it's exotic. Schools and universities are seizing the chance to build curriculum around Apophis. Orbital mechanics, gravitational perturbations, and statistical risk analysis become easier to grasp when tied to a visible point of light in the sky. Teachers can show how the scientific method works in practice. Initial uncertainty, hypothesis refinement, accumulation of evidence, and final confident prediction. The journey of Apophis from threat to certainty mirrors the scientific process itself, offering a model not just for astronomy, but for all evidence-based decision-making. Professional organizations are taking coordination seriously. NASA's Planetary Defense Coordination Office, ESA's Space Safety and Security Program, and the International Asteroid Warning Network have established unified guidelines for how Apophis should be discussed. Their protocols stress clarity, context, and consistency. Researchers giving media interviews are trained to lead with safety, to avoid jargon, and to present the encounter as an achievement of science rather than a brush with doom. These precautions are designed to ensure that the excitement of the flyby fuels scientific curiosity, not panic. The encounter also provides an opportunity to highlight the infrastructure that now protects Earth from genuine threats. The same telescopes and radar facilities that tracked Apophis into safety continue to survey the skies nightly, cataloging thousands of new near-Earth asteroids each year. The same international cooperation that ruled out impact now coordinates detection and mitigation planning for future threats. By presenting Apophis as a success story, planetary defense advocates can showcase the payoff of 2 decades of sustained investment in asteroid tracking and deflection research. Beyond the technical, the encounter invites reflection on humanity's place in the universe. Seeing a mountain of rock sweep by, harmless yet close enough to glimpse with the naked eye, reminds us that cosmic hazards are real but manageable. Risk does not vanish, but with vigilance and cooperation, it can be understood and mitigated. If the public comes away from 2029 not just awed by the spectacle but reassured in the power of science to confront danger, then planetary defense will have passed its greatest communication test yet. The success of this effort will not be measured only in the absence of panic, but in the presence of trust. If the public understands that proximity does not equal danger, if they grasp the difference between preliminary uncertainty and final certainty, if they appreciate the quiet, unglamorous work that made this confidence possible, then the 2029 flyby will leave a legacy far beyond its few hours in the night sky. It will be remembered as the moment when humanity learned not just how to watch the heavens, but how to talk about them wisely. Part 10. What comes after 2029? The spectacle of the 13th of April, 2029, will not mark the end of Apophis's story, but the beginning of a far richer and more consequential chapter. Its close pass by Earth will serve as a natural experiment in celestial mechanics, providing data that no simulation or laboratory experiment could ever match. In the months and years that follow, astronomers across the globe will continue tracking Apophis with obsessive precision, measuring every alteration in its orbital path, every subtle shift in its spin state. Earth's gravity will have left fingerprints on this asteroid, permanent modifications to its semi-major axis, eccentricity, inclination, and rotation. These changes, detectable with ground-based telescopes and radar facilities, will confirm in exquisite detail how gravitational encounters reshape asteroids over time. For planetary defense, these aren't just scientific curiosities. They are validation of the very models used to predict and mitigate impact risks. By June 2029, OSIRIS-APEX will arrive at Apophis, beginning an 18-month campaign to map the aftermath of its brush with Earth. The spacecraft, reborn from its earlier triumph as OSIRIS-REx at Bennu, will document every scar left by tidal stress, from potential landslides to subtle rearrangements of surface boulders. Its instruments will measure Apophis's altered gravitational field, catalogue its rotation rate, and conduct the bold thruster disturbance experiment, an artificial nudge designed to loft subsurface material into space for remote study. These operations will provide ground truth about how rubble pile asteroids respond to stress and disturbance. Such knowledge could someday spell the difference between a successful deflection mission and a catastrophic miscalculation. The scientific stakes are profound. If Apophis proves more coherent than anticipated, behaving less like a loose pile of gravel and more like fractured bedrock, future planetary defense missions may need to deliver far more energy than expected to shift similar asteroids off course. If, instead, it turns out to be looser and more fragile than models predict, then kinetic impactors may prove even more effective than hoped, as ejector from the surface multiplies the momentum transfer. Either outcome reshapes the engineering of deflection technologies, sharpening the tools we will one day need. Apophis, by surviving its passage past Earth, will teach us how to save Earth from its more dangerous cousins. Equally important is the international choreography behind this campaign. NASA, ESA, and observatories from every continent are already rehearsing their roles in the global observation effort. The coordination required to monitor Apophis's flyby will become the template for how humanity responds when the next asteroid appears not as a safe spectacle, but as a confirmed threat. Apophis is, in essence, a full-dress rehearsal, a harmless flyby that lets us practice the protocols, communication strategies, and cooperative mechanisms that a real emergency would demand. The collaboration alone is historic, an unprecedented pooling of resources and expertise focused on a single cosmic object. This test case will echo into policy as well as science. Apophis has already influenced how governments think about space safety. Its transformation from feared threat to scientific opportunity demonstrated the need for institutions dedicated to planetary defense. NASA's Planetary Defense Coordination Office and ESA's Space Safety and Security Program both trace their current mandates, at least in part, to the lessons of Apophis. After 2029, those lessons will harden into precedent. When future impact risks arise, There will be no ambiguity about who has the authority to coordinate response, who communicates with the public, and how decisions are made. Apophis will have established the playbook. The educational legacy will also be lasting. Generations of students will study Apophis as the archetypal case of how science confronts risk, early uncertainty, public alarm, sustained observation, and eventual certainty. The asteroid will become a case study, not only in orbital mechanics, but in risk communication, in the psychology of uncertainty, and in the necessity of evidence-based decision-making. By demonstrating science as a process rather than a pronouncement, Apophis offers a counterweight to the culture of instant answers and viral misinformation. Meanwhile, the technical infrastructure built for Apophis will continue safeguarding Earth. Radar imaging at Goldstone and Greenbank has reached resolutions fine enough to resolve surface features mere meters across. Optical astrometry is now so precise that it can detect the faint push of the Yarkovsky effect, nudging asteroids over decades. These capabilities, sharpened by years of monitoring Apophis, will apply equally well to thousands of other near-Earth asteroids still lurking in the sky. Survey missions on the horizon promise to expand that catalogue at unprecedented speed. NEO Surveyor, launching no earlier than 2027, will peer into the infrared, spotting dark asteroids invisible to optical telescopes. Its discoveries will likely number in the thousands, particularly in the hazardous 140 to 500 meter size range that Apophis exemplifies. The Virus C. Rubin Observatory, beginning operations in 2025, will scan the entire visible sky twice a week with unmatched depth and cadence. Together, these instruments will eliminate the blind spots that allowed Apophis to surprise us in 2004. Future Apophis-class asteroids will not arrive as sudden alarms but as well-characterized objects tracked for decades in advance. What comes after 2029, then, is not closure, but expansion. Apophis will no longer be the god of chaos, but the cornerstone of a new era in planetary defense, an era where predictions sharpen, technologies prove themselves, and international frameworks solidify. The asteroid that once terrified us will become the asteroid that trained us. And while the data from OSIRIS-APEX, from radar, from photometry and spectroscopy may yet reveal surprises, perhaps structural behaviors we cannot yet model, or compositional puzzles hidden beneath its weathered crust, those surprises will be absorbed into the broader arsenal of human preparedness. Even commercial space may find benefits. Understanding asteroid structures and surface mechanics is critical not just for deflection but for mining ventures, resource extraction, and future construction projects in space. Apophis may thus contribute not only to planetary safety, but to economic opportunity, expanding humanity's reach into the solar system. In the end, the post-2029 Apophis era will stand as a testament to what planetary defense has become, not the reactive panic of the early 2000s, but the proactive, globally coordinated science of the 2030s. Apophis will recede into the darkness of space, its orbit altered, its story transformed, but its lessons embedded in the systems, institutions, and knowledge that will protect us from the asteroids yet to come. Private companies are beginning to see asteroids not just as threats or scientific curiosities, but as potential resources. The same characterization techniques refined through 2 decades of studying Apophis radar imaging, spectral analysis, rotational mapping will someday guide commercial missions in search of water, metals, and rare elements on near-Earth objects. What we learn from Apophis about rubble pile structures, regolith cohesion, and compositional signatures may one day determine whether mining ventures succeed or fail. In this sense, the 2029 flyby is more than a planetary defense milestone. It is also a rehearsal for humanity's economic expansion into space. Public policy will feel the ripple effects as well. Apophis's transformation from terrifying possibility to scientific triumph demonstrates the tangible value of investing in asteroid research. Legislators who once balked at funding planetary defense will point to the Apophis case as proof of concept. Modest investments in surveys and modeling prevented panic, clarified risk, and produced a windfall of scientific knowledge. The argument for increased funding to expand telescope networks, launch space-based observatories like NEO-Surveyor, and support rapid response deflection mission studies will grow stronger in the wake of this encounter. The story also raises uncomfortable questions about law and governance. Right now, no binding international treaty defines who has the authority to launch a deflection mission if a genuine threat emerges. Apophis, safe as it is, highlights this vacuum. The coordination protocols developed for its observation shared databases, global networks, rapid communication channels could evolve into the framework for an international planetary defense authority. Policymakers will debate whether sovereignty, security, and liability should be defined before the next scare arrives. If Apophis becomes the model for cooperation, it may also spark reforms in space law to prepare for less forgiving scenarios. Even outside the halls of power, Apophis will continue to inspire. Amateur astronomers who track its orbit in the 2030 seconds and 2040 seconds will provide valuable citizen science data, supplementing professional observatories. High school students may use their own backyard telescopes to measure its changing brightness, contributing to long-term monitoring efforts. Educational institutions are already building curricula around Apophis, using it to teach not only orbital mechanics but also statistical reasoning and the philosophy of science. The lesson is universal. Knowledge emerges from patient measurement, uncertainty shrinks with evidence, and fear subsides when facts accumulate. The cultural impact will be equally enduring. In 2004, headlines cast Apophis as a cosmic serpent poised to destroy. By 2029, it will be remembered as a harmless streak of light across the sky, watched by millions. That transformation reflects more than improved mathematics. It reflects humanity's growing ability to understand and manage risk. It represents a shift in identity, from passive passengers on a vulnerable planet to active stewards capable of defending our home. The psychological resonance of that shift may inspire careers in science and engineering, shaping the workforce that will guard against the next Apophis. Future missions will likely target asteroids with similar characteristics, deliberately choosing objects that echo Apophis's size, orbit, and structure. By treating Apophis as the archetype for potentially hazardous asteroids, scientists will gain a benchmark against which to measure others. The convergence of recent breakthroughs underscores this readiness. DART-proved deflection works, OSIRIS, Apex, will show how a large asteroid responds to Earth's gravitational pull, and new telescopes will discover the next generation of PHAs before they surprise us. It is rare in history for technological capability, institutional coordination, and public awareness to align so perfectly. Apophis sits at the center of that alignment. Speculation about the unexpected adds anticipation. What if Earth's tides trigger dramatic avalanches across Apophis's surface, exposing untouched material? What if its rotation shifts in ways that models failed to predict? Even if nothing dramatic happens, the negative result will matter just as much, providing the constraints needed to refine theories. Either way, the asteroid will change how we think about rubble piles, internal cohesion, and long-term orbital evolution. The Global Observation Campaign itself may become the model for how humanity approaches other grand scientific challenges requiring worldwide collaboration, from climate monitoring to space-based solar power. The economics of Apophis are subtle but profound. 2 decades of surveys, radar campaigns, and spacecraft missions have cost far less than a single major terrestrial disaster, yet they transformed a potential existential risk into a controlled scientific opportunity. That return on investment, measured not just in data but in peace of mind, may be the strongest argument yet for funding planetary defense. Outreach campaigns will amplify this message. Teachers, science communicators, and museums will retell the Apophis story for decades, highlighting how scientific method turned fear into understanding. The narrative arc, uncertainty, alarm, evidence, and safety captures in miniature how science works and why it matters. The hardware and expertise developed for Apophis will remain in service long after the asteroid fades from headlines. Radar systems refined for meter-scale imaging, telescopes tuned for rapid tracking, and software capable of analyzing thousands of orbital trajectories simultaneously, these tools will now apply to the rest of the near-Earth asteroid population. They multiply the return on investment, ensuring that money spent for Apophis also protects us from as-yet unknown threats. Historians may one day mark Apophis as the inflection point when planetary defense matured. Before, humanity reacted piecemeal to scares like Tunguska, Chelyabinsk, and early Apophis uncertainty. After 2029, planetary defense became systematic, proactive detection, coordinated communication, and tested mitigation strategies. The asteroid that once terrified schoolchildren may be remembered as the object that taught our species how to survive cosmic hazards. Yet its legacy will also carry humility. For all our telescopes, spacecraft, and supercomputers, we remain at the mercy of celestial mechanics that have shaped worlds for billions of years. The next threatening asteroid will come. It is a question of when, not if. The true legacy of Apophis, then, may be less about the asteroid itself and more about the institutions it strengthened. International coordination, robust detection infrastructure, validated deflection technology, these are the insurance policies against catastrophe. They are investments in survival, tools we hope never to use but cannot afford to lack. Apophis has shown that threats can be turned into opportunities and fear into knowledge. The challenge now is to ensure that when the next warning arrives, we will be as ready as 2029 made us believe we could be. Part 11. Finale. As 3I Atlas fades back into the cold silence between stars and Apophis prepares for its once-in-a-lifetime passage by Earth, humanity stands at a decisive moment in its relationship with cosmic hazards. The juxtaposition of these two objects reveals not just the difference between what is spectacular and what is dangerous, but also the chasm between the threats we pay attention to and the ones that actually matter. 3I Atlas embodies everything we find romantic about the cosmos: rarity, mystery, the allure of an interstellar traveler. It blazes across the sky with a glowing coma, sparks headlines about alien visitors, generates a burst of research papers, and then vanishes forever into interstellar space. It is beautiful, fascinating, and utterly irrelevant to human survival. Apophis, by contrast, represents the mundane, an ordinary body of silicate rock and metal, tracing the same elliptical orbit for millions of years, indistinguishable from thousands of similar asteroids, except for the accident of its discovery and the brief terror it inspired. It lacks the drama of exotic origins, yet it taught us everything critical about planetary defense. Atlas teaches us about chemistry and alien systems. Apophis taught us how to avoid extinction. The irony is that our imagination is captivated by the object that will never return, while our civilization could have been undone by the one hiding in plain sight. This misalignment reflects a deeper flaw in how humans assess risk. We are wired to fixate on the novel, the dramatic, the once-in-a-lifetime event, while discounting familiar, routine dangers that accumulate silently. The lesson applies across the spectrum of space hazards. Solar storms threaten electrical grids, satellites, and astronauts. But public interest remains muted because they're part of the sun's ordinary cycle. Orbital debris grows each year, multiplying collision risks, yet rarely captures headlines. Even within asteroid science, discussions fixate on kilometer-sized extinction-class impacts, spectacular, yes, but far less probable than the regional city-killer asteroids in the 100–500-meter range that pose a much higher cumulative threat. This distortion in public perception has consequences. Funding for planetary defense must compete with other priorities, and that competition is shaped by what captures attention. Spectacular but harmless visitors like 3I Atlas draw fascination that, if properly directed, could be harnessed to support the systematic surveys and mitigation technologies we actually need. Apophis proves what can be achieved when scientists and policymakers take ordinary asteroid threats seriously. Decades of observation, international cooperation, and technology development transformed a potential catastrophe into a safe, well-understood encounter. The infrastructure that protects us now exists because earlier generations invested in mundane threats instead of dazzling curiosities. The NEO-Surveyor mission embodies this systematic philosophy. Unlike one-off probes of exotic targets, its purpose is to discover large numbers of ordinary asteroids in Earth-crossing orbits. Success will not be measured in spectacular photographs, but in catalogue completeness. The Vera C. Rubin Observatory, with its sweeping sky surveys, will map tens of thousands of near-Earth asteroids with unmatched precision. These efforts highlight the true work of planetary defense, not glamorous discoveries, but patient, continuous accumulation of knowledge. By contrast, 3I Atlas will flare briefly in our awareness before fading into silence, leaving behind little more than journal articles and fading headlines. The DART mission reflects the same pragmatic focus. Rather than chasing the exotic, it targeted an ordinary binary asteroid system because it offered the best chance to validate kinetic impactor technology. Its spectacular success in altering Dimorphos's orbit proved the principle of deflection, showing that with enough warning, humanity can change the trajectory of a cosmic threat. Frameworks like the International Asteroid Warning Network and the Space Mission Planning Advisory Group may lack dramatic appeal, but their quiet work, standardizing observations, coordinating data, preparing response protocols forms the backbone of global readiness. Communication remains one of the most delicate challenges. The media gravitates toward proximity statistics and superlatives, often framing encounters in terms designed to shock rather than to inform. Scientists must counter this by emphasizing clarity. Apophis will not hit Earth in 2029, nor for at least a century after. This message must precede every other detail, supported by scale diagrams and accessible explanations that show why closer than satellites does not mean dangerous. The opportunity should be used to build lasting scientific literacy, teaching people how to distinguish between provisional uncertainties and confirmed safety, between statistical possibilities and genuine risks. The economic rationale is equally compelling. The costs of systematic asteroid surveys and deflection technology pale in comparison to the devastation a single impact could cause. Yet, because these efforts require sustained investment over decades, they are vulnerable to complacency. Ironically, The very success in eliminating Apophis as a threat could be used as a pretext to scale back funding. That would be the gravest mistake. The real danger is not Atlas, and not even Apophis, it is the erosion of vigilance. The parallel with broader societal risks is unavoidable. Climate change, pandemics, technological disruption all represent slow-building, familiar threats lacking the drama of the spectacular. Yet they demand the same discipline of sustained attention, evidence-based planning, and global cooperation. Planetary defense offers a microcosm of how to handle such challenges, with physics providing clarity where social systems often stumble. The lesson of Apophis is that even existential-sounding threats can be managed through systematic science, international coordination, and patient accumulation of evidence. As Atlas slips back into the void and Apophis approaches its date with history, humanity faces a choice. Do we continue chasing the exotic, dazzled by interstellar visitors, or do we focus on the familiar neighbors whose paths truly matter? The universe is indifferent to our preferences. Asteroids follow Newton, not narrative. If we allow fascination with the spectacular to overshadow preparation for the ordinary, we risk losing the only home we have. If instead we choose to value vigilance as highly as wonder, then Apophis will be remembered not for the danger it once seemed to pose, but for the wisdom it forced us to cultivate. The final irony is that 3-1 Atlas may leave us with the most human of lessons. It reminds us of our instinct to marvel at the exotic and dismiss the ordinary, to chase beauty while neglecting danger. Apophis, meanwhile, demonstrates the opposite, that salvation often lies in the mundane work of measuring, calculating, and preparing. The true threat, then, isn't the asteroid from another star. It is the complacency that blinds us to the ordinary neighbors we can track, predict, and, if necessary, deflect. Wonder has its place, but when survival is at stake, wisdom must prevail.